Good deal.
Vibrating seats.
All right. Over this region right here. Y equals 16 minus x squared. Well, I might as well continue it. Okay. This is 0, 16. From 0 to 4, this is the region here. So, up above this region, we have this parabola that's moving down the y-axis, this thing that looks like this. We're finding the volume underneath that surface over this region. Liam.
So they picked an arbitrary function representing a y for which to mark the area on the xy coordinate that you're finding volume.
Yeah.
It just happened to be the same formula.
It happened to be. Yeah, that is a pure coincidence. Good call. All right, that's what we're doing. Or, another way to interpret this is, we're taking this y equals 16 minus x squared, okay, right here, and we have a density function of 16 minus x squared. The density function just happens to be equal to the function itself, and we're finding the mass of that object, okay, of that lamina, whose density function is 16 minus x squared. That's another way to interpret what we're finding with this double integral, okay? Two ways. Okay, let's do it. Bless you. So 0, let's integrate with respect to y. Substitute in. Substitute in 0 to give us 0. It's kind of cute the way this works out. Yeah, well, it's cool, because now you can factor out a 16 minus x squared and be left with a 16 minus x squared, which gives you a 16 minus x squared squared. And now we're going to do this integral, but unfortunately we have to multiply it out to do it. We don't have an x hanging out as our du, so we're going to have to multiply it out. So we get 256 minus 32x squared plus x to the 4th. It's kind of yuck here. Okay, and then integrate it, 256x, 32x cubed over 3. Okay, x to the 5th over 5. Okay, from 0 to 4, a little messy in here. Substitute in 4, we get 4 times 256, that's 1024, minus 4 cubed is 64 times 32. 64 times 32 is, I don't know, 64, we could do this, right? 64 times 32. 60 times it is 1920. 4 more is 128. That gives us 2048, I believe.
Yep.
And 4 to the 5th power is a 1024 again, I guess.
Yep.
Okay. Oh, boy. So we could put everything over 15. All right, so we get 15 times this. Nice problem, Omar. 5 times this. Okay. 5 times this is 40, 24, 2, this. And then a 3 times that, 12, 7. All right, I don't know what we get. We get something over 15. What do we get? Does anybody know? Get 15,000 minus 10,000 plus 8. Yeah, I need somebody to do that.
15,000?
Yeah, well, it's 15 times 1,024, so you get 15,000 and change. Then you get this 10,000 thing, and then you get this 3,000. I don't know. What do you end up with?
I see where you're going.
Hold on.
We're getting.
546. Oh, wait, shit. I already. That's if you divide it by 15.
Oh.
Answer 546.
All right, so this is 15 times that, so it's 546. Thank you. Thank you. Okay. Good job. Okay. Any other questions on anything?
Wait, so it's like a partial integral.
This is a double integral.
No, I'm just saying it looks like, if you're doing it to the x and you're doing it to the y.
Yes, yeah, it's exactly right. It is akin to the partial derivatives. It's the inverse operation to that. We're doing a partial integral with respect to y only here. X is a constant. Okay? Is this, we have disagreement?
Yeah, I disagree.
Teddy disagrees then, I'm sorry, but I got to go with Teddy.
I got a.
Got 5.6.
At this point, I just don't care. About what? I never get it right. Whoa.
Oh, you got it right.
What'd you get,
I
Teddy?
didn't get. I got like
546.
546.13.
Oh, that's good enough. That's good enough.
Yeah, I just like that addition where it's 1024 over 5. I forgot to make that addition. I kept it as a subtraction. So
There you go. He can fix it. There you go.
1333333.
That's fine.
Yeah.
That's good. All right, any others? All right, let's go on. Cool. Here's what we're going to do.
Spoken like a true physicist.
We're going to find, is that right? Centroid of lamina of varying density. That's what we're doing. Let's do it. Here's what we're going to do. We're going to take a right triangle. Okay. And what we want to do is find, first of all, we want to find the centroid of this right triangle with constant density. We'll do that first, and we can do that geometrically. Okay, we don't need calculus to do that. But then what we want to do is assign a density function to this, where the density is going to change depending on where we are in the lamina. And then we're going to see what happens to the centroid as we change the density function. Okay? So the first thing to do is let's find the centroid geometrically. The centroid of any triangle is the intersection of the medians. Okay? These two medians, now medians are line segments that go from a vertex to the midpoint of the opposite side. I could have this median as well. Well, I could draw it as well.
Well,
Okay? This would be 3, 3 here. Okay? Yeah, every triangle has 3 medians. The medians are always concurrent. They always intersect at a point. And that point is the centroid of that triangular region. Meaning what? If you were to cut this out of a piece of cardboard, it would balance on the head of a pin at that point. It means this: if you were designing a building and you had a triangular platform or something, and you needed to have a beam to hold that platform, you would erect that beam right at the centroid of that triangular platform. That's where all the weight all the mass can be considered to be concentrated at its centroid. Okay, that's where you would want to put that weight-bearing beam. Okay, at the centroid of that triangle. How do you find the triangle? Well, it's the intersection of the medians. What is that intersection? Let's find it. We need the equation of these two medians. The equation of this line is y equals slope -6 over 3, -2x plus 6. Okay, that's the equation of that line. The equation of the other median, this one over here, would be y equals, the slope of this line would be -1/2 x plus 3. Those are two medians. Let's find where they intersect. Actually, medians intersect at a point 2/3 the distance from the vertex to the midpoint of the opposite side. But let's find the point of intersection. Set the two equal to each other. Multiply by 2, I guess. Okay. 3x is equal to 6, x equals 2. If x is equal to 2, take either one of these two lines, find when x is 2, y is 2. we get this 0.22. Okay? That 0.22 right here. All right, hopefully I did that right. All right, that is the centroid of that triangular region, 2, 2. That's where that would balance on the head of a pin. Now, here's what we want to do. We want to change the density function to some constant to something that's not a constant. Let's take our density function, and let's say it's proportional to x. In other words, the greater the x-coordinate of the point, the greater the density, okay? As you move away from the y-axis, as you move away from this, it gets more and more dense. The densest point would be right at the end.
I
Yes?
just want to clarify, are you representing x's coefficient as kappa?
Yeah, that's a kappa. That, yeah, kappa. Why did I use kappa instead of just a k? I could have used just a k, but I went to the Greek kappa for some reason. I'm not sure why, Dylan. I could have just gone to k.
K accidentally.
Wait, actually, you could just say it's k, because that's what it is. It's a kx or kappa x. Kappa being the Greek letter k. All right, whatever. I don't know why I went there. It must be my genetic, because I am mostly Greek. I'm more Greek than Irish, even though the Burns name is the Irish part. But I'm more Greek than Irish. But anyhow, that's all right.
Appreciate it.
All right. All right, so how are we going to do this? Well, what you have to do here is to find the centroid. Recall what you did in Calc 2. This is a Calc 2 problem where you found the centroid of a lamina of constant density. And what you had to do there was divide the problem up into two parts. You had to find the mass of the lamina first. And then what you had to do is sum up all the moments from each individual axis. In other words, for a given here, let me just do this in general, then we'll apply it to our triangular region. Let's suppose we have some kind of object here. And what we want to do is find its centroid. Well, one thing to do, what we're going to do, one way to do this, is divide this up into little square sections.
Pork chop.
There you go. Pork chop. Somebody hungry or what? So let's take this one and let's find the mass, first of all, of that little square. That's, believe it or not, it's a square. The mass of that is going to be a delta x, a delta y, times the density function at that point. That's the mass of that object right there, that little square. What's the mass of the whole region, the whole lamina? Well, its mass is equal to the limit, as n goes to infinity, of the sum of all these little masses. Okay? And what that is a Riemann sum in terms of x and y. That's a double integral. That's what a double integral is. It's a double integral of our density function. dx dy or dy dx. I'm going to put dy dx. That's more usual. Okay? Well, that's the mass, but that's not the whole story. If we want the centroid, what a centroid is an average, okay, from the x-axis, the average of the moments generated by these squares from the x-axis. Well, let's find out what that is here. This square has a moment, the first moment. Let's call that, well, let's see. I want to sum up all the moments. Well, let's just do this. From the x-axis. Now, let's take this one first. This one moment generated by this square is equal to a mass times distance. That's what the first moment is. Okay? That's what we're concerned about. Mass times distance. This is what you did in Calc 2 when you developed this formula for constant density. What's the second moment? Not that we're going to go there. What's the second moment generated by this particular square? It's mass times distance squared. And third moment, it's a mass times distance cubed. All right? You guys know that stuff? That's that other thing. Okay, yeah, we won't even say it. All right. All right. This moment generated by this square is equal to the mass of this squared times its distance. Well, what's that distance that this square is from the x-axis? It's the y. It's the y coordinate. Okay? So here's what we have. We have a y, the y coordinate, whatever that y is, that's its distance, times the mass of this object, which is this density function, times a delta x, delta y, or delta y, delta x, either way. That's the moment that this one square generates about the x-axis. It's a mass times distance. What's the total moment from the x-axis generated by our region? It's the limit, as n goes to infinity, of the sum of all such moments. Okay? That's what it is. It's a Riemann sum in x and y. Again, how do you evaluate it? With a double integral. The difference is we have a y coordinate here. That is the moment generated by this lamina about the x-axis. It's the sum of all the individual moments. And what about the moment generated from the y-axis? That'll be the distance, x. So we have this. The moment from the y-axis. Everybody okay with this?
Just a sec.
Okay, okay. Wait, where's David?
Okay, I'm all set.
I hit him, new people.
HID, I think you said. Oh, I hope. Yeah, okay, good.
No, you hit him first, then you hit him.
Oh, jeez. That's not good. All right, moment from the y-axis is exactly the same thing except for our distance, which is x. Okay. Now, what is a centroid? It's an average moment. The centroid. X bar, Y bar. And that's what, you know, in statistics, when you see X bar and Y bar, that's, I don't it's the average. That's what the X bar means. It means the mean of the X's and the mean of the Y's. And that's equal to the average moment, which is what? It's equal to the sum of all, here, I'm going to write it this way first. The X bar is M sub Y over the mass. The Y bar is M sub X over the mass. Okay. What is the M sub Y? It's the sum of all the moments from the y-axis divided by the total mass, which will give you the average. It's a weighted mean is what it is. Okay? All right, you ready? That's the formula we're going to use to find the centroid of our lamina, our right triangle of varying density, where the density function is k or kappa x. Now, what do you think should happen here? If I have this as a density function, what should happen to the centroid? Should it stay the same? Should it move up, down, left, right? Where should it go?
Closer to 6, 0.
You bet it should. That's exactly what it should do, because that 6, 0 is our densest point on this triangle. And that centroid should move towards the 6, 0. Let's do it. All right, so let's find the mass first. Mass is equal to the double integral, our density function, okay, dy dx. The y's are going to go from, now recall what our function, what our lamina is here. Let me do this one more time. Okay. The y's are going to go from bottom to top when they hit this function. Well, we need the equation of this line now. That line is equal to a negative x plus 6. Okay. So the y's are going to go from 0 to negative x plus 6. The x's are going to go from 0 to 6. This will be the exact mass of this lamina. Integrate that, kxy. Substitute in. I can take the k out front. That's a constant. Substitute in for y, the opposite of x plus 6. That's k, 0 to 6. Now integrate that. 6x squared over 2. And that's equal to 6 cubed, 216. 216 over 3, 72. 108. Okay, 36 times 10, 108. And we get 36K. Okay, so the volume of that lamina of varying density is 36K, where K is that proportion, whatever that happens to be. Okay, let's do the moment from the x-axis. Everything is the same, except now we have a distance to involve, and that's y. Moment from the x-axis is y. Y is the distance. So we end up with kxy. But everything else is the same. But that y makes things a little bit more difficult to do. Okay, how are we doing? All right? You guys with me on this? All right. Let me pause a minute here. Okay. Pause a little bit. Okay. How are we doing, Adrian? You okay?
Wait, did you guys say that 60 is going to be the densest part of the triangle?
Yes.
Why is that exactly?
Because our density function is kx is proportional to the x coordinate. And that's the point with the greatest x coordinate.
Okay.
So if it's
ky, it should head up the other way to 0, 6. And what should kxy do?
keep it the same.
Nope.
I'll score.
It goes that way towards the hypotenuse. And it's really kind of cool because you know what they do? They travel right along the medians to their destinations. And if you do variations like x squared, y cubed, it takes a path that's somewhere in between, and it's really kind of cool. It does exactly what you would expect it to do. Well, let's verify that right now. Let's do this. Let's take the k out front. Let's integrate xy dy. No, it does get a little messy, though, I must say. Oh, well, it does get messy. Okay, so we get k, 0 to 6. Substitute in that, so we get x. We can take the 2 out front, too. Y squared. 0 gives me 0, so that's good. So we get k over 2, 0 to 6. I'm going to multiply that out. That gives me an x squared, so that's x cubed. That gives me minus 12x, so it's going to be minus 12x squared. That gives me 36, so it's 36x. Alrighty. I'm going to have to go to another paper. Oh, boy. These problems, they take a while. Everybody okay?
Yeah.
Here we go. What happened?
Gideon.
Get in, I lost you. No, you good? All right.
Take one for the team right now.
Oh, man. All right, let's integrate this with respect to x. We're going to have an x to the fourth over 4, a 12x cubed over 3, 36x squared over 2. Oh, 0, 6. Okay, 0, 6 there. That's equal to 6 to the fourth. Okay, well, 6 to the fourth is 6. What do we got? 1296? 1296, I guess?
Yep.
1296 over 4, which is 324, I believe. You guys better verify this. Okay, 6 is 216 times 4. Okay, that's 864. Plus 18x squared, that's 36 times 18. I don't know, what do you got? 648. Thank you.
If you just pull the kid over there, should be good at being a math major.
Yeah, that's it. That's what we do. You guys see that all right? Yeah. All right, so you end up with, what do you get when you do this? And divide by 2? What is it? 54K? All right, that one's 54K. Hopefully that gives us something we need. All right, so moment from the y-axis is equal to, let's do the other one, double integral, 0 to 6, 0 to 6. The distance now is x, so we're going to have a kx squared. Wow, okay, let's do it. 0 to 6. Integrate it. Kx squared y. 0, negative x plus 6. Okay, dx. Substitute it in. Bring the k out front. X squared y. 0 to 6. Negative x cubed plus 6x squared. That's equal to k. Negative x to the fourth over 4 plus 6x cubed over 3 from 0 to 6. I should have simplified that to a 2. 3 goes here once and twice. Okay, that's 2x cubed. Okay. Now, substitute in 6. I'll get 6 to the fourth. Okay. And we did 6 to the fourth, so we got 6 to the fourth is 1296 over 4, which I've already done. What is it?
324.
320. Thank you. And that's negative plus 2x cubed. And what is that there? 432. Thank you. And when I add those two together, I'm going to get 108. Yes, 108K. Now, that's the moment generated by this object about the y-axis. Here's what I have. My centroid, x bar, y bar, is the moment from the y-axis over the mass, moment from the x-axis over the mass, the moment from the y-axis, 108K. The mass is 36K. Moment from the x-axis, 54K. Over the mass of 36K. What happens? K's cancel. 108 divided by 36 is 3. And this is 3 halves, 1.5. Now, is this reasonable? let's see. If we go back to the original, here we are. And we had three medians. Here, here, and here. Our original median was 2, 2. If you recall, we had 2, 2. Our new centroid is 3, 3 halves. Now, the question is, it's clearly to the right and down. Is it right on the median? Well, it's easy enough to check. We know the equation of that line. The equation of that line is y equals negative 1/2 x plus 3. That's the equation of this median line. When the x here is 3, what do we get for y? We end up with 3 halves, which is exactly on this median. What happens to that median? What happens to the centroid? It travels along the median down towards that point. If we were to do a density function of kx squared, what would happen? It would travel along the median a little bit closer to 6, 0. And if we had kx cubed, it would travel even farther along the median. And if we had kx to the n, and as n goes to infinity, what would that limit be equal to? 6, 0. And I believe that's what your lab is on this chapter, is to do that limit as n goes to infinity. And not only that, if we had ky instead of kx, where would that centroid go? It would head up this line, up this median, up to this 0, 6 line. And if we had kxy, it would head along the median right to the middle of that hypotenuse of 3, 3. It's amazing. It's amazing
If it
stuff.
was just k, but it's 0, 0.
Say that again?
There's no y or x, which goes 0. 0, 0.
No. To get it down that direction, I think you have to get negative densities in there. Because right now, with a constant density, it's at that point. If you get negative densities, all bets are off. You get crazy things. I've had students do that.
But it's part of the triangle. You think it'd be more like.
I think it goes, I think you can get it outside the triangle if you have negative densities, I think. It seems to me I had one student a few years ago. Oh, well, yeah, you'd have to experiment with
Yeah,
it.
because with the negative density, you're basically repelling, so you could get
just
into
try
the
to-
Yeah, yeah.
trash and you can't.
Give it a shot. Do it on the lab is to do what we just did and have Mathematica draw it. It's really kind of cool. And then ultimately find the limit as n goes to infinity. But that's positive densities. You're welcome to experiment with negative densities and see what you can get. That's fine with me. Track the path with certain negative densities. That would be fine with me. All right, how are we doing? Nice. Okay, tomorrow, triple integrals. We'll get some volumes and masses and center of masses of these solids in space.
Okay, if it's a constant density, it's going to stay the same.
Yes.
Now, what exactly is causing it to move when it's transferring enough?
What's moving, because it's getting denser in this particular case. You got this triangle here. The densest part of the triangle is over here. The lightest part of the triangle is here.
How do we clarify this?
How we what?
How would we clarify this?
KX. The fact that it's KX tells us exactly
Why
that.
do we know that's KX?
I just gave it to you. I said, let's assume a density function of KX.
Based on the equation that represents the function.
Yeah. Yes, exactly. Exactly.